OSIRIS MSA on OSIRIS Opt. OSIRIS Natural Feature Tracking System has resumed processing. Position uncertainty is 1.6 meters. OREX MSA on OREX Ops. OREX has processed its next image. Position uncertainty is 0.9 meters. OREX MSA on OREX off. OREX has processed its next image. Position uncertainty is 0.7 meters. OREX MSA on OREX off. OREX has processed its next image. Position uncertainty is 0.6 meters. OSIRIS MSA on OSIRIS Ops. OSIRIS has processed its next image. Position uncertainty is 0.5 meters. OREX MSA on OREX op. OREX is slewing to the tag attitude, the third and final natural feature tracking attitude. OREX MSA on OREX op. OREX has reached the third and final natural feature tracking attitude. The spacecraft will hold this fixed attitude until tag.
actually called 16 Psyche. And this mission is going to arrive in early 2026 and help us better understand if this asteroid is potentially actually the core of a planet-sized object. We also have other types of asteroids called Trojans that are clustered in two groups that lead and trail in Jupiter's orbit due to a balancing act of the pull of both Jupiter's and the Sun's gravity on them. NASA has a mission to those Trojan asteroids called Lucy. It's going to launch next fall, about a year from now, and it's going to go visit several of these Trojan asteroids. We have a new mission called Janus, and we selected this mission through our Simplex small mission program line. This mission is going to send actually two small spacecraft, very small spacecraft, to two binary asteroid systems and help us understand what it is that makes these binary asteroid systems different from one another. And so studying this full breadth of these diverse small worlds will continue to help us fill up the knowledge gaps of how our solar system actually formed and evolved over time.
So it seems with all these missions coming up, we're sort of in a golden age of asteroid exploration. But then there's this other aspect of the OSIRIS-REx mission, which is the sample return. And it turns out that we're also beginning this golden age of sample return to it, and not just to asteroids.
You're absolutely right. And we're really excited about all of these samples because they're so precious and there's so much science we can do with them. In addition to OSIRIS-REx, we're also partnering with the Japanese Space Agency on their mission called Hayabusa 2, which is actually already on its way back, bringing a sample from Ryugu. They're going to be coming back to Earth in December. We're also partnering with Japanese Space Agency on another mission of theirs that's going to return a sample from Phobos, which is one of the two moons of Mars. And then finally, at the end of this decade, we're going to send a mission to Mars to retrieve the samples that are collected by the Perseverance rover, which is really truly our first astrobiology mission from NASA. And it's focused on looking for finding potential life, ancient life on Mars. So sample of return is really important because it allows us to study these pristine samples back here on Earth. We can then take advantage of our room-sized laboratories.
All of this. OSIRIS has begun moving the solar arrays to the Y-wing configuration to avoid possible contact with the surface during tag.
Great news, moving right along. So when we bring the samples back, this allows us to use all of the laboratory capabilities that we have here on Earth. We can use the full suite of the scientific instruments that we have at our disposal to help us better understand the sample, their compositions, and the history of the body from which they came. And also having the samples back here on Earth allows us to preserve them for future generations to come and allows our future explorers to analyze the samples using techniques and instruments that haven't been invented and to ask questions that we don't even know to ask yet.
That is just so cool. I mean, life is all about how we navigate unknowns. This is something that's happening in real time around us tonight. So it's reassuring to know that there's an organized plan that you're in charge of to help take some of the uncertainties out of at least one dramatic category. So Lori Glaze, thank you for joining us this evening. So good to see you.
Thank you so much for having me. I just want to add that it's been fantastic to watch the OSIRIS-REx mission so far, and I'm really, really excited for what's ahead tonight, and I want to say congratulations to the entire team.
Thank you so much.
Thank you.
Now, asteroids are not easily navigated. They're hard to see, they have low gravity fields, they're dark and rocky, and traveling around the solar system where everything is moving rarely means traveling in a straight line. Let's take a look at some of the big challenges the team has faced to get to this point.
As we started to approach Bennu from a distance and it started to fill up the camera field of view, it looked exactly like we thought it would, with a few boulders sticking out. But as we got closer, we expected to see a very sandy surface with maybe a few boulders here and there. And what we saw is very little sand. And we saw these mountains, we saw boulders, we saw rocks, and we saw very few areas that had this sandy surface that we were expecting and what we had designed to.
We have never done this before. We're actually going to collect a sample and bring it back down to Earth for further examination by scientists.
In order to achieve that objective, the OSIRIS-REx spacecraft has been navigating around Bennu for about the last 2 years, studying it in great detail, and also overcoming a number of challenges that Bennu has presented. We were looking for locations on Bennu that were 50 meters in diameter, relatively flat, and covered with fine-grained material. And by fine-grained material, I mean stuff that's the size of a dime or smaller. We realized that there were no sites on Bennu that even came close to meeting this criteria. Everywhere we looked was too small and covered with boulders. So we actually had to fly a number of additional close passes over the asteroid and rethink our entire plan for grabbing the sample. After the additional observations of Bennu, we had to down-select to 4 sites, and then go back and survey those sites even further to select the final primary sample site.
My first impression of Nightingale is that's the last place I wanted to go. But as we started looking at other sites, we saw that 1, this is probably one of the most sampleable sites, and 2, we were overperforming in our navigation capability and our ability to contact. Natural feature tracking works a lot like the human mind in that we pick up landmarks along the way. As we descend, we look at features on the ground. We program the computer to recognize certain features. It takes a picture, says this feature is not where I expected it to be, it's a little bit off to the side, updates its position based on where it's pointed and where that feature shows up in the camera position.
The tag event is our touch and go event, which is where we'll actually be retrieving the sample from asteroid Bennu. We start with a series of maneuvers, one of them being the checkpoint burn, which is where we'll actually check our position velocity in relation to the sample site.
And then the match point burn, about 10 minutes later, will zero out our horizontal velocity relative to the surface. And then about 10 minutes after that, we make contact with the tag SAM, fire the gas bottle, and then back away.
And we hope to get at least 60 grams of sample, and then we'll be able to store that and bring it back down to Earth.
But there are several things that could go wrong, and we also have to be prepared that we won't be successful on our first try at Nightingale.
We don't only get one shot at tag, we actually have 3 nitrogen bottles on board the spacecraft, so we can potentially do 3 tag attempts if needed. We go through several what-if scenarios, and this is how we actually prepare for a lot of our contingencies.
So we've had to look all around the surface and identify the rocks and boulders that if the spacecraft were to tip over up to 25 degrees, it could come into contact and be damaged.
We had to develop a hazard map, which we program into the computer and says, if you're getting too close to those hazards, we'll do a wave off, we'll back away from the asteroid, and we'll come back and do this another day.
Everything might work perfectly. We come down, we touch the surface just where we want to, we fire the gas bottle, but the area we contact is covered in large rocks. Those rocks would prevent any fine-grained material from being stirred up and captured in the tag SAM head. Another similar scenario is if the tag SAM were to touch on the edge of a boulder and become tipped up. In that case, when the gas bottle fires, much of that gas escapes out the side, not churning up the material that we want to capture. The day of tag is going to be really exciting, but the excitement for our team doesn't end there.
We have to verify that we have a proper sample.
First, we're going to image the tag SAM head by sticking it in front of one of the cameras. Then we're going to do a maneuver called the sample mass measurement, in which we stick out the arm and we spin the spacecraft in order for us to decide if we've collected enough mass to be able to stow the sample and return home, or if we have to try again.
This is the culmination of a lot of work. It's probably one of the most exciting missions that I've worked on.
It is really exciting to know that we're finally going to be able to touch the surface of the asteroid and collect the sample to return back to Earth.
So step back for a moment and realize that tonight's events are exceedingly rare and historic. Humanity has only landed on a few different bodies in the solar system, and actually retrieving a sample is even more rare. So luckily with me tonight are some of the people that know better than anybody all the challenges that it took to get here. So let me introduce Mike Moreau. Mike is the OSIRIS-REx Deputy Project Manager at the Goddard Space Flight Center, and Coralie Adam is Tag Navigation Manager at Kinetics Aerospace. So welcome, Mike and Coralie. How you guys doing?
So excited.
So excited. We're less than a half hour from tag now.
Yeah, you can feel the energy all building. So I should mention at this point that it's possible, you've been hearing this before, cheers from the MSA. So can you give us a sense what's going on right now?
Yeah, so every few minutes, a navigation camera image is taken by the spacecraft of the surface below, and it's sent to the Natural Feature Tracking System. And that system identifies features in the image and sends a signal back to Earth that it was successful.
Position uncertainty is 0.5 meters.
And the team celebrates. It tells us we're on track to our next target and on track to tag.
Absolutely. So now, clearly there's a lot to talk about in terms of the mission, but once again, you had to do all of this in the midst of this COVID-19 pandemic. So were there any mission expectations that changed? How did you deal with that?
Yeah, for sure. I mean, as the whole world was coming to grips with the pandemic in the March timeframe, this team was in the midst of preparing for our first TAG rehearsal, the checkpoint rehearsal that would take the spacecraft only 65 meters above the surface. So we had to rethink the entire way in which we were going to do that rehearsal with only a skeleton crew here in the building and with many of our team members remote, as Sandy mentioned before. Today we have people literally all over the building monitoring, also at Goddard Space Flight Center and at the University of Arizona watching this event today. But thankfully we got through checkpoint rehearsal in April and match point rehearsal in August.
And all those special considerations, they're still going on around us today, right?
Yeah, I mean, you could see people spaced out in the MSA when you were over there. And, we had more time to prepare for TAG in order to accommodate that and get everyone into the building here today. So I'm just incredibly proud of our team for, their efforts to keep the project on track for TAG in spite of all of these challenges.
Absolutely. So I know NASA's famous for having to deal with unexpected situations, and this COVID-19 thing is kind of a different flavor of unexpected situations. So we're going to deal about that. Okay, so now let's talk more about the challenges of TAG that we introduced in the video segment. So Corley.
Right, so you've seen that Nightingale site is an extremely challenging spot to navigate into. There's boulders all around it. This is totally different than how we originally designed the system to target a 50-meter diameter area. Nightingale is 10 times smaller than that. So it required the whole team to rethink how to safely navigate into the contact with the surface, and we had to come up with some new ideas.
Yeah, so the original navigation approach used LiDAR, or laser-based navigation, to take us to the Nightingale crater. But when we saw what Bennu looked like, we realized we had to switch to a vision-based approach, and that's the NFT system that you've been hearing about.
Yeah, so the Kinetics navigation team has spent the last 2 years learning how to navigate around Bennu using optical navigation techniques very similar to what NFT is doing on board the spacecraft today. So Kinetics worked with scientists and the Lockheed Martin NFT
OSIRIS
team
MSA on
to
OSIRIS
map the surface of Bennu.
OSIRIS has processed its next image. Position uncertainty is 0.5 meters.
Really honing in. So we mapped the surface of Bennu to unprecedented resolution of 2 centimeters per pixel, which is better than what we've done on our own Earth and Moon. So it was a huge Herculean effort to get to this point where we're comfortable handing the maps and the keys over to the spacecraft to get us down into this small site today.
Absolutely. So I guess right now it's time to say goodbye to you guys. The best of luck for today. I'm really excited, and it's great to be with you guys.
Thank you, Michelle.
Yeah.
Thank you.
So right now, I think probably the best thing to do is to check in with Gary Napier. I guess we're going to go back and see how things are going back there. So to Gary.
So things are going really good right now, Michelle. We're actually going to talk to Heather Enos here,
OSIRIS
the Deputy
MSA
Principal
on
Investigator
OSIRIS
for the
solar
OSIRIS-REx
arrays are
mission
in the
out of the
Y-wing
University of
configuration.
Arizona. Thanks for joining us, Heather.
Hi, Gary.
So what's really interesting, Heather, is that you actually feel that, long missions like this are really important. I mean, you go from design to build, but operations is really quite a while, that it's actually really important to involve that next generation and kind of bring that generation up, correct? Talk to us a little bit about that.
Absolutely, Gary, you're right. All the way back from when we started planning this mission, OSIRIS-REx, we recognized it's a long duration mission. And although that presents challenges for retaining your key personnel, we actually took it as an opportunity to use this mission to train our next generation of students and science engineers and scientists. A good example is we had one of our science instruments is called REXUS. It's an X-ray spectrometer built by a team of students at MIT and Harvard. So real hands-on.
That's really interesting. I mean, I understand you also have some folks that actually were students and came onto the team later?
Yeah, so being at the University of Arizona on a PI-led mission, we have had hundreds of undergraduate and graduate students working on this mission over the course of the last decade. And 2 of our students that start off as students are actually 2 of our navigation team members. That's Dan Wibben and Eric Sarr.
Wow,
so
they're on console.
They're on console right now.
Right.
Yeah, they are.
At this time, NFC has
so
computed the checkpoint and matchpoint burn updates to correct for errors in the trajectory accumulated since orbit departure. Checkpoint burn in 2 minutes.
So checkpoint turn in 2 minutes. We're going to throw it back over to Michelle, because I know this is an important update for her. So Michelle, thanks. Back over to you.
Thanks, Gary.
Well, absolutely. So Dante, tell us what this important milestone checkpoint means.
This is a really important part of the mission right now. So we've been hearing about natural feature tracking and how it's processing these images.
OSIRIS MSA on OSIRIS Ops. OSIRIS has processed its next image. Position uncertainty is 0.46 meters.
Right, so what it's doing with that information is it's calculating how it's going to fire its thrusters for this checkpoint. When we left orbit, we were on a trajectory that would take us over the surface of the asteroid, and if nothing else happened, we would safely fly past Bennu. Once we fire the thrusters for the checkpoint maneuver, we're actually going to start descending down towards the asteroid surface, so this means we're going to be on our way to make contact. So natural feature tracking has been doing nothing but calculating this maneuver since we started taking images.
So this is one of the big deals. This is one of the big milestones coming up
This
now.
is huge.
Yeah.
Absolutely.
I know that as we look at the simulation, there's an interesting configuration the spacecraft is in. Oh, I see the thrusters firing.
That's right. You can see we would expect right now on the spacecraft the thrusters to be firing, so we're going to be paying close attention to Dale Howell to let us know we've gotten telemetry back to telling us that maneuver has succeeded.
In the meantime, if you want to tell us a bit about the configuration it's in, go ahead.
Yeah, we heard Dale call out earlier that the spacecraft was in the Y-wing configuration. There we just reconfigured the solar arrays to get them up away from the asteroid surface, basically to protect their active areas from any dust loading that might be kicked up during the tag event.
It's another excellent Star Wars reference.
That's right, always. You can also see here in the simulation the Nightingale sample site, now down in the lower corner here. This is our target. This is what we're trying to get into with that spacecraft. So.
And it looks like there's a lot of boulders around that.
Yeah, as we've said, generally the surface of Bennu is rough and rugged and covered with boulders. Nightingale really does stand out as a pretty unique, interesting area on the surface.
How you doing?
Doing pretty good. I've been paying close attention to that call out, waiting for Dale to tell us that checkpoint has occurred.
Absolutely. So what we're waiting for right now is the call out that checkpoint has occurred, and the OSIRIS-REx spacecraft has begun its descent towards the asteroid surface.
Right, any time now.
And it's probably worth mentioning
OSIRIS MSA on OSIRIS Ops. Checkpoint burn has completed.
Okay, we're heading down towards the asteroid surface at this point.
Oh, wow. Oh, wow. Okay, well, you know, I guess the next thing that comes up is going to be this match point maneuver. So that's the next big milestone for us.
That's right. So we've got one more firing of thrusters with the spacecraft to get us lined up for the sample acquisition event. We call that the match point. Because what we're doing there currently as we're flying over the asteroid surface, in fact, it's the asteroid surface that's rotating underneath us. Mm-hmm. And when we fire thrusters for match point, we're doing that to match that rotational velocity so that the spacecraft becomes station keeping essentially over that Nightingale sample site.
Mm-hmm. Absolutely. All right, so I think we have a little bit time now to turn to our social media desk. So James, what's going on in social media?
Yeah, Michelle, it's super exciting. You just heard that checkpoint burn confirmed. We are now just very, very close down to the surface of Nightingale. And you guys have been really excited over on social media too at that hashtag to Bennu and back. Lots of great messages rolling in here. Someone's really excited for our little robot friend to go rock hunting on the surface. We had someone who actually attended our launch back in a couple of years ago, Cape Canaveral, and are now watching the broadcast live with us today, excited for that sample collection event. We have Philip, who kind of puts it in perspective for us here. He says, this is amazing and extremely difficult in so many ways. Bennu's orbit, spin, inclination, the orbital mechanics of this long mission are just astounding. I can only imagine how many orbit simulations have been made here on Earth. It really is a crazy mission, and we also have our animal friends, our pets, cheering us on here as well. Bennu is rough from this couple of our pets here, really excited. So we're now just minutes away from that match point burn, and for that, I'll kick it back to you, Michelle.
Okay, excellent. So, you know, just a few minutes ago, Dante, you were saying that this landing site is sort of a unique area on the asteroid. Tell us about this site.
Yeah, we spent an enormous amount of effort selecting the area on this asteroid surface where we wanted to get the sample from. And we kind of divided our analysis up into 4 different categories. First, we were looking at the deliverability. And this was a real challenge because, as we've seen earlier in the broadcast, the original guidance accuracy was 25-meter radius, and we're trying to get into an area that's 10% of that size. We have solved that problem with our amazing natural feature tracking solution, and as we've heard, that's worked really well, and it has updated its checkpoint and its match point maneuvers on board based on that information. That gets you down to the surface of the asteroid. So the next thing that we have to worry about is maintaining spacecraft safety. There's a lot of hazards on this asteroid surface, things that could damage a critical component, and we decided to focus safety on the things that were needed to get the sample back to the Earth. So there were certain things we could lose at this point in the mission if they didn't fulfill that objective. We still have some upcoming major milestones that help us maintain that spacecraft safety. Now natural feature tracking is going to be switching over to calculating the contact point on the asteroid surface. And it has a piece of software on board called the hazard map. It's actually determining, is the location that I'm going to touch down on safe, a green area on that hazard map, or is it potentially hazardous, a red area on that hazard map? So as we get closer to the asteroid surface, a key moment is the 5-meter crossing. That's when the spacecraft makes that decision. Do I continue down to collect the sample, or do I back away and live to tag another day? After that, you've got down there, your spacecraft is safe. There's got to be something for you to pick up. Earlier in the broadcast, Bo Bierhaus showed us the size of particles that TAGSAM could actually collect. So we had to map the Nightingale area and other potential sample sites well below that 2-centimeter resolution. And in fact, we got 3.5 millimeters per pixel all over the Nightingale sample site. And we were really excited to see lots of particles of that size. And of course, the final parameter that we were looking at was the scientific value. And I can tell you the good news is any sample from Bennu is scientifically valuable. We've seen these hydrated clay minerals, we've seen organic molecules, carbon-bearing minerals all over the surface of the asteroid, exactly the kind of material that we're hoping to bring home.
So I understand the next big milestone we're looking for here is something called match point.
That's right.
So what happens at match point?
Match point is the final maneuver that the spacecraft performs by firing its thrusters. And that's where we become centered over the Nightingale sample site and begin that final descent down to the asteroid surface. And the spacecraft is solely focused on its safety calculation and the decision on whether or not it's going to proceed down to collect that sample.
Of course, the amazing thing about match point is that the asteroid itself is actually rotating. So when we go to match point, the spacecraft has to match the rotation of the asteroid so it comes directly down onto it.
That's right.
So how fast is Bennu rotating?
Bennu has a rotation period of 4.3 hours. So that's basically the length of the day on the asteroid. On Earth, the rotation period is 24 hours, which is why a day on Earth is 24 hours long. So that translates, because Bennu's a pretty small object, as we've seen, 500 meters or about the same size as the Empire State Building. At the equator, the surface is moving at 10 centimeters per second. And it actually gets slower and slower as you go to higher latitudes. By the time you get to the North Pole, it's 0. Nightingale's pretty far north, so it's actually much lower than 10 centimeters per second. And that just kind of shows you the delicate precision nature of this mission. You know, we've got to get very low thrust maneuvers, very delicate, very slow approach to the asteroid surface. Everything kind of happens in slow motion when you're operating in a microgravity environment like Bennu.
So what's the next critical milestone after match point?
After match point, we're going to be looking for the natural feature tracking system coming back online, taking those images and additional correlations and precision on its knowledge of its position. And we might expect it to actually jump up. We've been hearing natural feature tracking uncertainties on the order of 0.5 meter. It may go up a little bit as it goes through.
on OSIRIS Ops. OSIRIS Natural Feature Tracking System has resumed processing. Position uncertainty is 1.6 meters.
So you can see there we went back to 1.6 meters. That's because we went through the checkpoint maneuver. So whenever you impart a thrust like that, it adds uncertainty into the system. And we're seeing that with the natural feature tracking system right now.
That is so exciting. Okay, so we're going to introduce, actually, the Associate Administrator of NASA, Dr. Thomas Zurbuchen. Thomas, thank you for joining us.
So glad to be here with all of you.
It's an exciting time, Thomas.
Happy birthday.
Thank you.
Yesterday,
That's right. Yesterday's his birthday. Yeah, that's right. Happy birthday. So, I guess, everybody here is aiming for this point in time called, this TAGSAM. But it turns out that there have been a lot of friends, a lot of colleagues that have helped get us to this moment. So, who's been along with us on this journey?
Well, look, I mean, there's a number of course, domestic partners, many of them around here. You talked to some of them, but there's also international partners. And the Canadian Space Agency provided the laser altimeter, which is an important instrument here. And of course, we have a partnership with JAXA. What we're going to do is actually share the samples from Ryugu, from Hayabusa 2, with OSIRIS-REx once it's back for maximum science. And that's really what international partnerships are about.
So this is a big mission for NASA, but it turns out that there are many different kinds of partners in a mission like this. Give us a sense of the range of partners that we have.
Well, look, I mean, it starts with the University of Arizona. That's where the leadership is, and with you there and your entire team. But NASA Goddard Space Flight Center is a critical partner with managing, of course, especially also working with Lockheed Martin, who really, with that team deserves a lot of credit, and Kinetics, which was already introduced, as well as many others. If you really look, so often missions like that touch many, many states around the United States.
Absolutely. So, Thomas Zurbuchen, thank you for joining us, and we will see you later on in the program.
How do you feel, man?
I'm pretty excited. This is the final 10, 12 minutes here for contact. I feel really good. The team's in high spirits. As you and I talked about earlier this week, we have done everything possible to make this today a success.
Exactly right. And your mind is already out there, and the spacecraft is already on the way out in real time. Can you imagine that, right?
It's good actually to point out whatever has happened with TAG has already happened. We're well past that 18.5-minute one-way light time.
Absolutely. Hey, congrats. Let's continue doing this.
Yeah, we'll see you later. Thank you, Thomas.
Yep.
Oh, wow. Okay, so we're coming up, I know, on the critical point of match point. So
That's right.
At what point will we know that we really have a sample?
That's a great question. We're not exactly sure what's going to happen right away. We'll know if we made contact with the asteroid surface today. We'll know if the gas bottle fired, and we know that we backed safely away from the asteroid. But we actually have a lot of work to do over the next week or so. We'll take a look at the images that we were acquired during contact with the asteroid surface, and then we'll go into a different imaging campaign. We're about 30 seconds from match point, so we're going to keep our ears open for that critical call out from Dale.
OREX MSA on OREX Ops. OREX has processed its next image. Position uncertainty is 1 meter.
All right, we're back down to a meter positional uncertainty. That's great news. So back to sample verification. We will, after we're well away from the asteroid and everything has kind of settled down, we have that robotic arm. We're actually going to use that to put the TAG SAM head into the field of view of SAMCAM. And we can look not only at the top of the sampler head like we're going to get with the images today, but we can actually turn it around and we can look at the base of TAG SAM. We have, in addition to the gas stimulation, we have contact pads. Simply by making contact with the asteroid surface, we think we can pick up fine-grained particles less than a millimeter or so. But basically, we're going to be looking for any evidence of asteroid material on or inside the TAG SAM.
Now, obviously, you don't want to go all the way back to
OREX
Earth without...
MSA on OREX Ops. Match point burn is complete.
All right. We're heading down. We've got about 10 minutes before contact with the asteroid surface.
Oh, wow. So I was about to say, so obviously you don't want to head back to Earth with not much samples. How do you know how much sample you actually got?
There's an incredibly clever physics experiment that the team has designed here called the sample mass measurement. So what we're going to do is we're going to place the spacecraft arm out to the side of the spacecraft. So when it's in sampling configuration, it's actually pointed above. For this, we point it out in the other direction and we kind of spin the entire spacecraft around. And we're measuring a property called the moment of inertia. We have actually already done this prior to initiating the TAG sequence today. So we know what that property is when the TAG SAM head is empty. Now we're going to be able to do it, hopefully, when it's full of asteroid regolith. So we're only looking for small differences in this property as a result of this experiment. And the precision, just like everything on this program, is phenomenal. We're talking tens of grams of precision on a measurement on a spacecraft hundreds of millions of miles away that just picked up this asteroid sample. The minimum that we're looking for is 60 grams, or about 2
MSA
ounces.
on OREX Ops. Attitude control system has transitioned to touch and go mode.
Right, spacecraft's getting ready to make contact with the asteroid surface here. So the sample mass measurement will tell us if we have 60 grams or more of material, and that'll happen on Saturday later this week.
Excellent. Okay, Dante, this is it. You know, the engines have given us a push in the right direction, and OSIRIS-REx is on course to make touchdown on an asteroid. So we're going to listen to the flight controller calls from MSA, but before we actually touch the surface, it's a great time to visit our social media desk again. So, James, what's going on?
Yeah, thanks, Michelle. So you've been hearing those call-outs from Dale over the loudspeakers about those NFT images processing. It'd be awesome to actually grab a camera and make the trek out to Bennu to photograph it up close in person. But, you know, as we've mentioned, Bennu is a little bit far away from us right now, on the order of 200 million miles away. But don't worry, here's something OSIRIS-REx can deliver to you right now from the comfort of your own home. If you're on Instagram, you can head over to @NASA Solar System. We have 2 AR filters that you can use on your social media stories. This first one's called OSIRIS-REx and You and features OSIRIS-REx playing tag with Bennu around your head. The second one is called To Bennu and Back and allows you to place an asteroid wherever you are, at home, at school, bring an asteroid with you. So I understand we actually have a question coming in from Instagram from Mauricio, who asks, how do you manage the force back from touching down? I mean, the moment the spacecraft touches the surface, it should experience a similar force in the opposite direction. How do you manage that? Well, thanks Mauricio. So the team actually thought ahead for this one when designing that sample arm. They actually added the spring-like mechanism to it that you can think of a bit like a pogo stick. If that sample arm were rigid, when contacting Bennu, it would stop its downward motion, and when firing the gas bottle to stir up a sample, we would just kick right back off into space, as Bo Bierhaus had mentioned earlier. But since we had that spring, you can think of it like a pogo stick. When you make contact with the ground, the springs start compressing and you keep your downward motion. It's same exact thing applies for OSIRIS-REx. When we contact Bennu, we continue moving downward, and when we fire the gas bottles, that actually slows our downward motion, giving us just enough time at the surface, on the order of maybe 10 seconds, to stir up a sample before we kick right back off into space. So if you actually want to see what the tag event is going to look like up close in person, we actually released a really cool 360 video on our NASA Goddard YouTube page that parks you
OREX
right
MSA
on Nightingale.
On OREX Ops. OREX has processed its next image. Position uncertainty is 0.5 meters.
Wow. So this is really, really high detail right now. We're getting really close to the surface. And again, like I was saying, if you want to experience what this is going to look like up close, park yourself on the surface of Nightingale and look around. This whole terrain is actually generated using real terrain data, down to 2 centimeter per pixel resolution. And as was mentioned earlier by Coralie, that is actually higher resolution than we've actually imaged our own Earth and Moon. So really, really beautiful imagery, and I definitely encourage you to check that out. But we're just minutes away from this actually happening in real life. So for that, let's kick it back to you, Michelle.
Okay, thanks, James. So, Dante, I want to ask you a couple personal questions here. You've spent about a third of your life working on this mission. What are you feeling now?
It's a pretty amazing emotional state, Michelle. When you get to a point like this in your career, an event that you've worked for, in my case, over 16 years to get here, you kind of think back to all the people who have helped you. I think about my family. I know they're watching from Tucson, Arizona right now. They've been really important to me. And another person who can't be with us here tonight, unfortunately, is my mentor, Dr. Michael Drake. He's the one who invited me onto this program in 2004 to be his deputy. I was a young, bright-eyed assistant professor, and we worked together for 7 years writing proposals to convince NASA that this was a program to fly for New Frontiers 3. We won the contract for OSIRIS-REx in May of 2011, and Mike passed away September, a real blow to the team. So I miss him. I wish he was here today.
Yeah. It's very real. I mean, you know, we're connected to our avatars that we put out there in the universe. So,
I know he'd be proud of us, and he would really love it to be with us right now.
So we're looking at sort of an amazing simulation right now. So, you know, as we mentioned before, these are not actual images from the spacecraft, but these are based on a huge amount of real data. So we're actually looking down as this TAGSAM instrument starts approaching its sample site.
Yeah, we are collecting tons of images right now, but we simply don't have the data rate to get them back to the Earth in real time. So they're just getting banked into the spacecraft's memory, and we're going to start looking at those later tonight and have them available for everybody tomorrow morning. So this is just a simulation of the field of view of the SAMCAM, the sampling camera, part of our OCAM's camera suite. It has a clear shot of the TAGSAM collector right in the middle of its field of view. You can actually see the lower end of the TAGSAM arm here.
OREX MSA on OREX OS. OREX is descending below 25 meters.
Okay, we're getting really close. And I want to remind you, it's the 5-meter crossing. That's the really critical one. We're only a couple minutes away from that. So the spacecraft has one key decision left to make. It's calculating right now the probability that it's going to come down either on a hazardous area, as we defined on that hazard map, or in a safe area. So we may, at 5 meters, the spacecraft may decide that it's hazardous and it's going to back away, allowing us to live the tag another day. So to me, all my senses are on that call out right now. I really want to hear that we are go for tag, so that's just a couple minutes away here.
And of course, remember that was planned for. That it has to know it's safe, otherwise it's going to back up and try again another time.
That's really how we solve the amazing challenges that this asteroid surface presented to us. You can see here that this is a pretty daunting terrain that we're coming down here. There's giant boulders all around the Nightingale site, even some large rocks inside the crater that we do not think the spacecraft would survive, at least with the ability to return back to Earth if it made contact. So it is there to protect itself first and foremost. Safety is always first, but we're feeling pretty good. Everything's gone really well today, so I would say things are looking great for a tag, but of course the spacecraft is the one that gets to make that decision.
It's just amazing. We've been rehearsing this event, all week long, all the different mission calls and milestones, but then to actually be here tonight and realize that this is going on 200 million miles away.
That's right, yeah. I'm pretty excited.
So, I mean, there were obviously a lot of firsts in this mission.
OSIRIS MSA on OSIRIS Ops. OSIRIS has processed its next message. Position uncertainty is 0.5 meters. Predicted tag lateral offset is 1.7 meters. Hazard probability is 0%. Tag lateral velocity is 0.2 millimeters per second.
Oh my God.
Tag vertical velocity is 10.2 centimeters per second.
That sounded really good.
Yes.
So it sounded like the hazard map calculation looks really good. That we're coming down on a green area. We're going to make contact with the asteroid surface.
Oh, wow. So remember how historic this is NASA's first mission to retrieve a sample from an asteroid, a pristine part of the solar system.
That's
Just
right.
Look at that animation now. So we're looking
I'm looking at the team. I think that, I think we can see everybody is laser focused on what this spacecraft's going to do. So I say let's let this play out. But those calls were really great. That was great news from Dale.
Yeah. Even more accurate than we'd hoped for in some cases.
Everybody seems happy.
Yeah. So I guess there were obviously a lot of firsts in this mission, and there was a time when you said a lot of what ifs basically. I mean, what if we could actually send a spacecraft to an asteroid? What if we really could bring back a sample of the solar system from billions of years ago? Do you remember where you were when those what if questions?
OSIRIS MSA on OSIRIS Ops. OSIRIS has descended below the 5-meter mark. The hazard map is go for tag. Contact expected in 50 seconds.
We're going in. We're going in.
Touchdown declared.
All right.
Sampling is in progress.
Oh my gosh, we're there, folks. That was amazing. I mean, I don't know if you saw the team here, but they just kind of blew up. They went from being steely-eyed to like celebrating the Super Bowl. So, it's all good. This is amazing. So congratulations, everybody. I know that Dante and Dr. Zabrukin are right here. And Dante, you somehow got over here pretty quick.
I sure did. Yeah.
Congratulations. How you guys feeling?
Transcendental. I mean, I can't believe we actually pulled this off.
God, I'm so excited about the team.
Yeah.
Hey, do you mind if I just bring up something?
Please.
Our friend Mike Drake is with us right now.
That's
the
right.
guy who came up with the mission at the beginning, and we're thinking of him. He's no longer on Earth, but I feel him right here.
I agree. He's with us today, and I know he's incredibly proud of this team and everything we have accomplished. This is history. It's amazing.
God, I can barely speak. I'm like shaking. How about you?
Absolutely. It's almost hard to process everything that's happening right now. It's overwhelming pride in this team and everything we've done to get here. I couldn't really have anything better to say about this group of people.
I'll say synthesis systems, I can confirm that the backaway burn is...
OSIRIS MSA on OSIRIS Ops. Sample collection is complete, and the backaway burn has executed.
All right.
We're on our way back.
Now, Dante, that was actually a really important call. We were celebrating on the tag, but that was actually probably even more important call. Why is that?
The pyro bottle's fired, so tag SAM operated. The backaway thruster's fired, so we're safely moving away from the asteroid surface. The spacecraft did everything it was supposed to do. So we did it. We tagged the surface of the asteroid, and it's up to Bennu now to see how the event went.
What does this mean to NASA?
Oh, I mean, this is the key milestone of this. Now it's a few days, right? To figure out how much we caught of this amazing sample that we're thinking about for decades. But I think this is just, I'm so proud of this team. Hey, team.
Oh, my goodness.
Oh my goodness.
Well, I got to tell you, this has been a fantastic day, a fantastic journey. We're so proud of both of you for being here and supporting that team. We're going to get back over to the stage and Michelle, but some really good news. So back to you, Michelle. Thank you.
This is one of those moments we're all aware of COVID-19 because I want the hugs and the high fives and everything, but we're all going to keep each other safe. There are lots of super excited people all over who want to share in this moment and share their congratulations.
No kidding.
So let's take a moment to hear a few words from 3 institutional leaders who couldn't be here tonight, but they're cheering on the team on behalf of so many supporters.
Hi everyone, Dennis Andrusick, Goddard Center Director. I am just so excited that OSIRIS-REx is collecting a sample from the surface of Bennu. The tag is just the pinnacle of the mission so far. Getting the sample back to Earth is obviously going to be the great event of the entire mission. But I got to congratulate Dante, you and your team, your project management skills as a PI, just superb. Rich, the operations team for getting us to where we are, and Lisa Callahan for the awesome Lockheed Martin team, and getting OSIRIS-REx to where we are, and building a great spacecraft and returning it to Earth. Go OSIRIS-REx.
Today's an exciting day. As OSIRIS-REx begins its descent to Bennu, the nation is looking forward to the news of a successful tag event. OSIRIS-REx team members have been working on this project for more than a decade, and the work being done is hard, and it's complicated, and it's necessary. Understanding the makeup of Bennu will help us better understand our universe and how to protect our most important asset in space, Earth. I want to wish the best of luck to the entire OSIRIS-REx team, including our partners at the NASA Goddard Space Flight Center, the University of Arizona, and especially the mission operators and engineers right here at Lockheed Martin. Go OREX!
The University of Arizona is incredibly proud of its long tradition of excellence and leadership in space exploration. I'm thrilled to see the OSIRIS-REx's mission's achievements carried this tradition forward today with NASA, Lockheed Martin, and all of our incredible partners.
Congratulations to all of the OSIRIS-REx mission team members. You have shown the world how our determination, creativity, and talent can advance the capabilities of our entire nation. And I can't wait for the amazing science we will see with the sample return in 2023.
Okay, well, we are here live after some excellent news. I'm here with an exultant Dante Loretta from the University of Arizona. So one more time for our audience out there, explain when we know we'll have a sample.
A little overwhelmed right now, Michelle, I have to say. It's been pretty intense several minutes here. I can tell you that everything went just exactly perfect, which is kind of the hallmark of this team. We have consistently beaten expectations over and over again. We have overcome the amazing challenges that this asteroid has thrown at us, and the spacecraft appears to have operated flawlessly. We made it down to the asteroid surface. We were in contact. The gas bottles fired. We don't know how long we were in contact with yet. That's some reconstructed information that we're going to have to put together over the next few hours as the data come in. We backed away successfully from the asteroid surface. The team is exuberant back there. Emotions are high. Everybody is really proud, and we have some work to do to determine how much sample that we have collected. The next thing that I'm going to be looking for is once the spacecraft cools off, it probably got pretty warm as it approached the asteroid surface, so it needs to get rid of some of that excess heat. It's got to get those solar rays back onto the sun and get power positive. Once it's stabilized, it's going to point that high gain antenna at the Earth, and we're going to start bringing that data back. And those SAMCAM images are going to tell us an enormous amount of information about how the events of today went. We're going to be looking at a whole series of images as we descended down to the surface, made contact, fired that gas bottle, and I really want to know how that surface responded. We haven't done this before, so this is a new territory for us. And the whole science team, I know, is really looking forward to that information. For one thing, it'll tell us the likelihood of sample collection, kind of a probabilistic assessment. Probably be a lot of science that comes out of that as well.
Yeah, well, listen, I know you want to be back there with your team. It's going to be a long, hopefully happy night for all of you as more data comes in. Thank you so much. It's been such an honor to be with you.
Thank you. Thank you, everybody, for a great evening, and kudos to this team. It's an amazing experience.
Oh, wow.
And in history, was made tonight.
Absolutely. So, you know, what we're going to do now is actually take a closer look at this beautiful terrain that we've actually sampled. We've identified over 1 million asteroids in the solar system. But remember, Bennu is what's called a NEO, a near-Earth asteroid. So instead of orbiting in the main asteroid belt between Mars and Jupiter, it has an orbit fairly similar to our own planet, Earth. And it not only gets our attention because it's so close to Earth, but also because we believe it may be one of the older bodies in the solar system with a wealth of information about how the solar system and life began. Let's take a closer look at the subject of all of this activity, all of this joy tonight.
Thank you.
Let's take a tour of Bennu.
In December 2018, after traveling for 2 years, 101 days, and over 1.2 billion miles, NASA's OSIRIS-REx spacecraft arrived at its target, near-Earth asteroid Bennu. OSIRIS-REx is the first mission to explore this primitive remnant from the origins of the solar system, designed to study the asteroid and return a sample to Earth. Bennu is a dark, diminutive world, roughly the height of a skyscraper, and now the smallest body to be orbited by a spacecraft. Prior to arrival, it was known to have low thermal inertia, a characteristic of fine-grained materials like sand. An infrared spectrometer on OSIRIS-REx confirmed this property, leading scientists to expect a predominantly smooth surface. But the first close-up views of Bennu delivered a major surprise. In exquisite detail, the mission's cameras revealed an unrelenting rockscape dominated by boulders. By combining these images from OSIRIS-REx with its laser altimetry data, we can take a tour of Bennu's remarkable terrain. The first stop is Simurgh-Saxum. This prominent boulder defines the asteroid's prime meridian and serves as the basis of its coordinate system. In Persian mythology, the Simurgh is a large and benevolent bird and the possessor of all knowledge. Saxum is Latin for stone. To the northeast lies the largest boulder on Bennu. Measuring over 300 feet in length, Rock Saxum is a colossus longer than a football field. It is also rich in a type of iron oxide called magnetite, which was used by mariners as an early form of magnetic compass. In Arab folklore, the rock is an enormous bird of prey that can clasp elephants in its talons, as well as stranded sailors like the hero Sinbad. Continuing northeast over the equatorial ridge, we arrive at Gargoyle Saxum. This striking boulder is among the darkest on Bennu, though it clutches a much brighter rock that is about the size of a person. In medieval legend, gargoyles are dragon-like, winged monsters that can breathe fire and that guard cathedrals from evil spirits. Our next destination takes us far to the east. At the northern end of a small crater lies Ocypity-Saxum, a comparatively bright boulder measuring about 33 feet in diameter. Ocypity-Saxum is located near one of 3 sites where Bennu ejected small particles into space in early 2019, displaying its dynamic and evolving nature. In Greek mythology, Ocypity is one of the 3 harpies, the half-maiden, half-bird personifications of storm winds, who would carry evildoers away from the earth. In the creation stories of ancient Egypt, the universe began as a formless, endless expanse of water. From this primordial sea arose the primordial mound, Benben. It was upon this rock that the god Atum settled in the form of the Bennu bird and sent forth the call that shaped creation. The story of Benben harkens to the mounds of fertile silt that once emerged from the receding floodwaters of the Nile, and it provides a fitting namesake for the tallest boulder on Bennu. Protruding by over 70 feet, Benben-Saxum is so tall that it was first detected from Earth. Now, we can appreciate this monumental feature in detail using data from OSIRIS-REx. The final stop on our tour is a cluster of exceptionally bright boulders scattered across the southern hemisphere. They bear the spectral fingerprint of pyroxene, a mineral found in igneous rock that is unlikely to have formed on Bennu. These boulders most likely originated on the large asteroid Vesta and were delivered to Bennu's parent body through meteoroid impacts. Although it is small in size, Asteroid Bennu has proved to be a fascinating world, abundant in geographic features that have defied our expectations. Thanks to OSIRIS-REx, we can now explore Bennu to uncover its composition, its evolution, and its ancient memories from the origins of the solar system.
And if everything has gone right tonight, a little bit of Bennu will be coming back to Earth in 2023. So let's get one last visit with our social media desk. James, what's going on?
Yeah, Michelle, I've got goosebumps. I really can't even begin to fathom that we just tagged and collected a sample from this asteroid 200 million miles away. I know I'm going to want to relive the events that just unfolded tonight, and I'm sure you will as well. So once again, we have that 360 video up on our NASA Goddard YouTube page. Go check it out and put yourself right where the action just happened a couple minutes ago. It's truly mind-blowing stuff. I also want to check back in with that Twitter poll that we put out at the beginning of the broadcast, and we were asking you how much material you think we just got from asteroid Bennu. So remember, we're looking for at least 60 grams, but that sample container can hold up to 2 kilograms. So you guys are saying that a candy bar size of sample. I like the optimism. Let's hope we actually pack that container to the max and bring all the sample back home. But any sample we get back is truly magical and will help us learn more about the solar system and our origins here. So keep at us on the hashtag to Bennu and back. We're excited to keep this conversation going as we look to bring that sample all the way back from Bennu here to Earth in 2023. So back to you, Michelle.
This is one of these evenings where it's such a privilege and a pleasure to be working for NASA and for the idea of scientific exploration. So what we've been doing all evening is seeing the joy, seeing these people that have worked on this for decades. But you have to remember there's a real reason we're going to look at these asteroids. We think we actually might be coming back with a baby picture of what the solar system was like, of what our chemistry was like billions of years ago. We're looking for our own origins out there, and that's why we've gone so far to bring a bit of Bennu back. This has been an incredible evening. The adrenaline is slowly beginning to slowly go down, and there's going to be a lot of celebration and a lot of work in the coming hours. So from Lockheed Martin Space here in Littleton, Colorado, I'm Dr. Michelle Thaler. Good night.